In this example, we will show how a right shift can be used to implement a divide by 2, and we will discuss unsigned versus signed operations, and then we will show or consider dropout, which is the loss of information that occurs on a right shift or divide by 2. Let's begin. In this example, we are asked to implement the function m equals n shift twice, where m and n are 16-bit unsigned variables. If we were to write this in C, we would define unsigned variables using the unsigned and 16 bits using the short, and we'll give them the names m and n. The function that shifts n to the right by 2 is shown here, and that result is stored into m. For example, if n were equal to 1,000, then we shifted it right 2. That's the equivalent of dividing by 4, and the result would be m equals 250. In assembly language, we will define the 16-bit variables into RAM, in our case in address 800. And we will specify the size of the variables with an RMB2, or reserved multiple bytes 2. 2 bytes will be required to specify or to store the 16-bit variable. Notice we did not define whether it was signed or unsigned. More about this later. To perform this function, it will be a 3-step operation. The first step is to bring the initial value of n into register D. Now we've selected register D because it is a 16-bit register equal in size to the 16-bit variable n. Now, when we execute the load D instruction, the initial value, signified here with the bits A15 down through A0, are loaded into register D. The second step is to perform the operation, which in this case is to shift right twice, and we'll do that with a shift instruction. The L stands for logical, which means unsigned. We're going to shift it right, which is equivalent to divide by 2, and we're going to shift register D in this case because we have a 16-bit shift. After we execute the first shift instruction, we notice that a 0 is shifted in to the left-hand side, and the A0, the last bit, is shifted out. That A0 is lost. When we execute the second shift operation, another 0 is shifted in on the left. This time, we've lost the initial bit A1. The A1 is shifted out and lost. The third step of this sequence is to store the result into the variable m. And the value in register D is copied into register m, and we're done. The initial value in n was shifted right twice, and the result stored in m. Notice that we have lost 2 bits of information. The information bits 1 and 0, initially in n, are lost after we divided or shifted right. This loss of information is called dropout, which occurs whenever we divide or shift right. Information is discarded at the bottom side as we shifted the bits. In order to look at dropout in another way, let's consider the example of 7 shifted right twice. In other words, assume that n had the initial value of 7. In binary, 7 is 3 ones here at the bottom. We see that after we execute the shift once, a 0 is shifted into the most significant position, and all the other bits are shifted over 1 position to the right. That causes the most significant bit here to be shifted out and lost. When we execute the second shift, again, a 0 is shifted into the most significant position, all the other bits are shifted 1 position to the right, and another 1 is shifted out. We get the result of 7 shifted twice is equal to 1. Remember, the shift right is the equivalent of divide by 2, and so this operation is the equivalent of a 7 divided by 4, and we get the result of 1. We know that 7 divided by 4 isn't 1, but this error or this incorrect answer is an example of dropout. because the bottom 2 bits were lost. Next, I'd like to consider the difference between unsigned and signed operation. In C, we specified an unsigned operation by defining the variables as unsigned. In assembly language, we specified that it was unsigned because we used logical shift right D, the unsigned shift right. With an unsigned number, the variables m and n exist between 0 and 65,535. In contrast, when we use a signed number, the numbers go from minus 32,768 to plus 32,767. In C, we define the operation as signed by showing or defining that the variables are signed variables by using just the short. When we perform the operation right shift in C, we don't tell it whether it's signed or unsigned. That was previously specified because we defined m and n as signed. Notice the operation of right shift in C for an unsigned and a signed are identical. However, in assembly language, when we perform a right shift, we use the arithmetic shift right, which is the signed shift right. In an arithmetic shift right, notice we don't shift in the 0 bit, but rather the initial most significant bit is copied or shifted in again, such that after the first shift, the top 2 bits are equal, whether it be a 0, 0 if the number were positive, or a 1, 1 if the number were negative. When we shift it a second time, a second copy of the sign bit is shifted in. Notice that the sign bit of the initial value n, which is A15, is copied or restored every time I do a right shift, such that a negative number shifted right will always be negative, and a positive number shifted right will always be positive. In summary, in assembly language, we specify whether a number is signed or unsigned by the selection or choice of instructions we used. The logical shift right D is an unsigned shift, and the arithmetic shift right D is a signed shift. Next, let's consider overflow. If n is a 16-bit unsigned variable, then n could range from 0 to 65,000. If we divide it by 4 or shift it right twice, then we'll get a number which exists from 0 to 16,000. In each case, regardless of what n is, the result m will always fit back in to the 0 to 65,000 range. Therefore, this operation does not overflow. So, in summary, we use the right shift to implement a divide by 2. In assembly language, we specify whether an operation is unsigned or signed by the choice of instruction. The logical shift right instruction here is unsigned. In assembly language, we specify whether the operation is 8 or 16 bits, the precision of the operation, by the selection of the register we use to operate. In this case, we chose register D because these are 16-bit operations. And third, we saw that as we shifted bits to the right, the bottom bits were shifted out and lost. This loss of information that occurs with a divide or a shift right is called dropout. Thank you very much.